Okay, so for course outcome 4, our topic would be electrostatics. We aim to use Coulomb's law to calculate the electric force between static charges, distinguish electric force and electric field, to calculate the electric field due to a collection of charges. Like charges repel, and like charges attract. The force of attraction or repulsion between two charges is inversely proportional to the square of the distances between them. Okay, so this is the basic structure, no, of an atom. So for a proton, the mass, which is a positive charge, it has a mass of 1.673 times 10 to the negative 27 kilograms. For neutron, which has no charge or neutral, mass is 1.675 times 10 to the negative 27 kilogram. And electron, which is negatively charged, has a mass of 9.109 times 10 to the negative 31 kilogram. The conservation of charge states that the algebraic sum of all the electric charges in a closed system is constant. Charge is neither created nor destroyed. It is merely transferred from one object to another. Electric charge always occurs now as an integral multiples of E, which has a value of 1.602 times 10 to the negative 19 coulombs. For uh, like charges, no, for both positive and negative, the the vectors or the forces are directed away, no, from the atom. And for unlike charges, the forces are directed towards each other. According to Coulomb's law, the force is directly proportional to the product of the charges, no, and inversely proportional to the square of the distance between the two particles. So, for example, here the distance between these two particles is denoted by r, and k has a value of 8.988 times 10 to the 9 Newton meter square per Coulomb square. The electron and proton of a hydrogen atom are separated on the average by a distance approximately 5.3 times 10 to the negative 11 meter. To find the magnitude of the electric force and the gravitational force between the two particles, calculate the ratio of the uh, magnitude of the electric force and the gravitational force. Okay, so from the previous slide, the proton has a mass of 1.673 times 10 to the negative 27 kilogram. For electron, the mass is 9.1099 times 10 to the negative 31 kilogram. And since we're also asked for the gravitational force, we'll be needing the gravitational constant, which is 6.67 times 10 to the negative 11 Newton meter square per kilogram square. And then the value of Q, or the charge for each electron or proton, is 1.602 times 10 to the negative 19 Coulomb. And then the constant K is 8.988 times 10 to the 9 Newton meter square per Coulomb square. Okay, so from Coulomb's law, we know that F is equal to K times the product of Q1, Q2 divided by the square of distance R. Okay, so this is the value of K, and then the charge is 1.602 times 10 to the negative 19. Since it is the same for proton and electron, so we have to square the value, divide by the square of the distance. This is the value of R. So the electrostatic force is 8.2 times 10 to the negative 8 newtons. And for the gravitational force between the two particles, proton and electron, the formula would be G times m1 m2 over r squared. M1 m2 are the masses for proton and electron. This is the gravitational constant, G, and the square of the distance. And then computing, we get 3.6 times 10 to the negative 47 newtons. So the ratio between Fe and Fg will be 2 times 10 to the 39. Okay, let's have another example. So 3-point charges are located at the corners of a right triangle where Q1, Q3 are the same at 5 microcoulomb, and Q2 is negative 2 microcoulomb, and distance A is 0.1 meter. So find the resultant force experienced by Q3. Okay, so we have three particles here. Q1, which is a positively charged, Q2 is negatively charged, and then Q3 is positively charged. Okay. Distance A is 0.1 meter. Now this is also A. So this forms a right triangle. So by Pythagorean, this is the hypotenuse, no? So square root of A squared plus A squared is square root of 2 multiplied by A. That is the distance between these two positively charged particles. We're asked to get the resultant force, no, from this particle. So uh, the force between uh, this particle negatively charged and then this positively charged. So since they I mean the force should be directed towards, no, so unlike unlike charges, so the force should be directed towards q2, and then the electrostatic force acting between q1 and q3 is denoted by F13. Now since these two are positively charged, then the force must be directed, no, away from Q3. Now, obviously, this is 45 degrees, no? This is a right triangle. So, this is directed 45 degrees uh, up up to the right. Okay. Now, we compute first for the electrostatic forces F23 and F13. So, using Coulomb's formula. Okay. And that's the value of K. So, using this formula, okay, we compute for F23, your Q1 is 5, this is 5 times 10 to the negative 6, okay, and the other one is negative 2 times 10 to the negative 6, but we take the absolute value, so you get a positive value for F23, no? Your A is 0.1 meter, and then for F13, Q1 and Q3 the same. So the value here will be 5 times 10 to the negative 6 raised to the power 2. This is the value of K, and then your R again is 0.1. No. Your A is 0.1, but see, we take the distance between Q1 and Q3, which is square root of square root of 2A. So, i-square natin to dito, no? So, your R here is square root of 3 times A is 0.1. And you should get 11.2, okay, for F13. Now, how do we get the resultant vector acting at Q3? Okay, so since this is directed to the left in vector form, we have negative 8. This is 8.99, so negative to the left, so we have a negative sign here, and then this vector I here, the unit vector I here denotes that the force is directed to the left. That is directed along the negative x-axis. And then no y component, so you have 0j here, but no need to write. Okay, and then for F13, this is directed up to the right, so positive x component, that will be, so your F13 is 11.2. So 11.2 times cosine 45 degrees, the x component, and then that is, since this is the x component, so multiply by the unit vector I, and then for the y component, that will be the magnitude 11.2 times sine 45 degrees, then multiply by j, because this one is your y component, the vector directed along the y-axis, and then the resultant vector, let's say F3, is the sum of F23 and F13. Okay, so for the x component, that is negative, for F23, no, negative 8.99i, and then plus 11.2 cosine 45 degrees, that will give you 1.04, And then for the y component, the y component will only come from 11.2 times sine 45 degrees. So you should, which is 7.94 or 7.94. So this is your resultant vector acting at Q3. Okay, how can objects move even without any visible force acting on them? These are some illustrations. So contact forces usually will come from tensile forces, frictional forces, normal forces, spring forces. Some would be caused by gravitational forces, electric forces, magnetic forces. Electrostatic force exerted on a small positive test charge placed at a point divided by the magnitude Q sub O of the test charge. Okay, so this is the behavior when you have a positive point charge, and as you can see, the field lines are directed radially outward, and then for a negative point charge, the field lines are directed radially inward. And the electric field is given by this formula, no? Directly proportional to the charge of the particle and inversely proportional to the square of the distance r. Okay. The density of the lines is proportional to the strength of the fields. Okay, let's discuss example number 3. So charges Q1 and Q2 are located at x equals negative A and x equals A respectively. Okay, so this is the y-axis. So this is a distance from the y-axis. This charge is a distance. Negatively charged is a distance from the y-axis. Evaluate if Q1 and Q2 and Q are equal. Evaluate the electric field, no, at this particular point, 0 y. So this distance is y. And then directed on the located on the y-axis, which is y units from the x-axis. Okay. Okay. The electric field, you have a positively charged, it should be directed now away from the charge. So this is passing through P. This will be the direction of E1. And then this is a negatively charged, so directed towards the charge. So this must be the direction of E2. E must be the resultant vector, no, of E1 and E2. So if this is angle theta, this is also angle theta. You can compute for theta since A is given, Y is given, then you can compute for theta by tangent function. So Y over A is tangent of theta. So you can get the direction of E1 and E2. Okay, so for the y component of E, so the y component will come from E1 and E2. This is positive, directed upward. And then using the formula for E, which is K times Q over K times Q over R squared. No? Your R this is your R, the distance between P and uh, this positively charged particle, which is square root of A squared over Y plus Y squared. No? Pythagorean theorem, because this one is a right triangle. And then the charge is Q, and then multiplied by sine theta. Okay, for the y component. Okay, and for E2, this is negative. This is directed downward, so you have a negative sign here. Same charge Q, and then same angle, so sine theta multiplied by the charge Q. And then the distance is also R. This is also R. And as you can see, the sum would be equal to 0. And based on the diagram, your E is directed to the right. So no Y component. No? E has no Y component. And for the X component of this, obviously this is positive. So that will come from the X component of E1 and E2. So using again this formula, but this time we get the X component, so multiply by cosine theta. No? Multiply by cosine theta. And simplifying, we have same quantity, so just multiply by 2. But take note that your R is square root of A squared plus Y squared. No? So in terms of R, and we can simplify it to K times 2QA over RQ. Okay? So take note that this this is actually your E, which is purely based on EX, uh, which is directed to the right, so it has no Y component. So given K or QA and then the distance R, you can compute for the electric dipole. Okay, so this will be left as an exercise.